second to last day of the conference. So I just wanted to mention before we get started that there will be a group photo immediately following the first talk, so don't run away, just head straight outside and we'll take your photo, and then everything will be, you can go ahead and have snacks after that. So our first speaker will be Damaris Schindler, who will speak on integral points on degree 4 del Pezzo surfaces.
Thank you. So first I would like to thank the organizers for the invitation. All right, I want to start with a very classical theorem due to Hasse and Miskowski. So assume you're given an integer coefficient quadratic form, say q in n variables, x1 to xn. Say that join x1 to xn. And you want to understand and ask the question, does q equals 0 have a non-trivial solutions in the integers or not? So I assume this is a homogeneous quadratic form. Say in variables. Then you learn some kind of number theory course, say that q represents 0 non-trivially over the integers. If and only if it represents 0 non-trivially locally for every local place, or in other words, if and only if you can find a non-trivial 0 over the real numbers and modulo every prime powers. So if and only if q represents non-trivially over R and modulo every prime power. So this last condition could also be restated as saying you have a non-trivial solution in the p-adic integer set P. That's the same thing. I formulated here in this way for integer solutions. Since Q is homogeneous, it has a non-trivial integer solution if and only if it has a non-trivial rational solution. This is homogeneous, it doesn't matter if you talk about rational or integer solutions. So I write it in this form because I want to ask another question. So, well, why do we need this homogeneity assumption in here? Or what would happen about non-homogeneous situations? So you can ask the same question for any quadratic equation Q, where we just drop the condition Q being homogeneous. So let me give an example which in this form is due to Schulze-Pillow and Xu. Take n and m, natural numbers, which I assume to be co-prime. Say k as a natural number, at least 1, and assume that n is concurrent 5 modulo 8, and that 2 divides m, but 4 does not divide m, so 2 exactly divides m. Then you can consider the quadratic equation, say c and m, given by m squared x squared plus n to the power 2k y squared minus n z squared is equal to 1. Then we can observe that this quadratic equation has the property that, well, first of all, you have a real solution. And also, modulo every prime power, one can solve this thing. In other words, there are non-trivial p-adic solutions for every prime p. But there are no global solutions. The set of integer solutions is empty. So it's easy to see that there are local points. For that, you could conveniently look at 2 points which are, well, rational solutions. 0, 1 divided by n to the k, and 0. They both clearly satisfy the equation. And since I've assumed n and m to be co-prime, one of them is a point for set p for every prime p. So that's what gives you very quickly the local solutions in this case. But in this example, well, as stated, there are no global points, and there's different ways to explain that. So one way how we understand such things classically is via genus theory. But I want to give you the following explanation for this, which is moving more towards the point of view that we want to take today. There are no global points. You could consider the following as a Maya algebra. Given by 1 plus n to the k y with the discriminant n. So the observation is that if you had a point x, y, z with integer coordinates, then you could stick this point into the symbol. You could view that as a Hilbert symbol for every, say, prime p, the infinite place. And then we know it by the Hasse reciprocity law that if you have a Hilbert symbol, say, for place nu, where nu is now the product of all places of q, so nu is either infinity or prime p. And if you stick into these Hilbert symbols two rational numbers, then by the Hasse reciprocity law, the product over all places has to be equal to 1. So in particular, if we take this example, if you had a point x, y, z, then 1 plus n to the k times y, comma n, has the property that you get 1 if you take the product over all places. But on the other hand, what you can do is you can fix, say, 1 prime p here, and look at the periodic points, the periodic solutions to the equation C and M. And then you can compute what does the Hilbert symbol give you, what values. What you will find is that this is always constants on the periodic points. You always get 1, except at the place p equals 2, where you get always minus 1. So what you find is that if you had an integer solution, it would have to satisfy this relation. But you find that there are no local points satisfying this relation. So as mentioned before, there's a classical way of explaining such things. This way of approach can be seen as explaining this phenomenon of the failure of the Hasse principle with a so-called integral Brauer-Manin obstruction. That's what I want to introduce in this talk now. The advantage of this formalism is that you can extend it to other situations very easily. And the goal of this talk is to study such obstructions, such failures of the local global principle for systems of two quadratic equations, not necessarily homogeneous in 4 variables. But before I come to that, let me first formally state what I mean with the integral Hasse principle. Definition. What is relevant for us, you could take, say, any system f1 up to fr of polynomials need not be homogeneous in, say, n variables. Then you can define the scheme over spec z and affine n space formally. Or more concretely, you can just think of it as you look at a system of equations f of x1 up to xn is 0 for all I. And you ask about integer solutions. And then we say that the integral Hasse principle P holds for x if we find a non-trivial integer point as soon as there are local points everywhere. So if there's a real point and there are periodic solutions for all primes p. So it's just the same statement as if you would talk about a Hasse principle for rational points. So questions that one is interested, of course, is when does the integral Hasse principle hold, under what conditions? Which is also computationally relevant because the conditions locally then can be checked. It's a computable problem. So if the integral Hasse principle would hold, then you could have an algorithm to figure out if you have a set solution or not for those systems for which it does hold. And if it does not hold, what are obstructions to it? Yes, please.
What is an Algebraic algebra?
So you can.
Does it have two generators there?
Yes. So formally, you would start with an Algebraic algebra over the function field of that variety, which I've written down. So you consider the variety, say, over Q rationals. And then it's first an Algebraic algebra over the function field. So it really lives in a Brauer group over the function field with the additional property. So if it's defined as over the function field, then you know it exists sort of in some open subset or on a generic point. And then you would have the additional, we would additionally postulate that it extends to the whole variety. That would be one way to talk about it. Yeah, that's just a quaternion algebra. Thank you. Yeah.
Do you want to say or instead of and for some kind?
Not an empty meaning? Yes. Yeah. So an observation that was made by Colliot-Thélène and Xu in a paper which appeared in 2009 is that such examples as above, which were already classically known, can now be explained with a so-called integral Brauer-Manin obstruction. The examples of the form above. So-called integral. So that you can have such Brauer-Manin obstructions to the study of rational points, thing that is much older, which was observed by Manin in the 1970s, that many such examples that one had in literature could be explained by such a formalism called the Brauer-Manin obstruction. So the new thing that Colliot-Thélène and Xu observed is that it also creates obstructions to the study of integral points, not just rational points. So let me recall how this works. So I write X if I think about the system of equations just defined over Q. So I base change it to Q, a variety over Q, the same thing, but think of it as a rational variety. So associated to a sufficiently nice variety X is its Brauer group, which formally is defined as a second étale cohomology group, but we will not really need, or we will not use this definition now for the talk, so I just put it here. What is important for us right now is that there's a pairing between the Brauer group and the adelic points, the so-called Brauer-Manin pairing. So you have a map which takes an element in the Brauer group of X, and on the other hand, an element in the adels of X, maps it to Q modulo Z. So you could think of a point here in the adels. I define it a little bit informally here. You would, in a way, not need to talk maybe about integral models of X, but in a way you can think of this as points where you have for every place a local solution. So the X news, they would need to solve your equation over Q nu for all nu, and you ask to make an adelic point out of it in a way for this X nu, the solutions being integral almost everywhere except for a finite set of places. So you would ask for X nu being, say, a set nu point for almost all places V. And then the pairing is defined by you take an element in a Brauer group and such a collection of, say, local solutions to the system of equations. And what you can do is you can locally, for every x nu, and formally it would be a morphism, say, from spec q nu to the variety x, so you could pull back the Brauer class, get an element in the Brauer class of the local field q nu, the completion, and which we know is for finite places isomorphic to q mod z by a local class field theory by the invariant map. That's exactly what you do here. So if you fix a place nu, then you can take the evaluation of this element at a place, and then you can sum up all the evaluations. Or more concretely, if you think about this quaternion algebra in the middle of the board, then this would mean that if you fix a prime p, say, you would stick in your periodic point into this Hilbert symbol. Computing this Hilbert symbol is sort of taking this evaluation, and then summing up corresponds to taking the product. That would be roughly the process, how this is defined. Then one can define the so-called Brauer-Manin set. It's a subset of all the adelic points. So if you ask for a global point, and of course, you need to assume you're locally soluble. The Brauer-Manin set is a subset of these adelic points, namely, this is the set of all the adelic points with the property that under this Brauer-Manin pairing, they all map to 0. So with the property that the evaluation is 0 for all elements alpha in the Brauer group of X. Then the observation, which Manin made in the 1970s, is that the rational points by this Hasse reciprocity law, saying that this product has to be 1 in the middle of the board, all the rational points, if you view them diagonally, embed them in the adelic points, then they're all orthogonal to the Brauer group, so they all live in this Brauer-Manin set, which is a subset of your all adelic points. And so that's the way how the Brauer group can obstruct the integral Hasse principle. You could have here local points which are, say, integral everywhere, but none of them could be orthogonal to the Brauer group. So this set could be empty, although you have local solutions everywhere. Then you don't find an integral point as well. Now let me give a remark of what is now different to the which did I? Oh, I'm not talking about those two. I mean, those 2 points, they would be legitimate points as well. They're rational points. I mean, they're integral almost everywhere. But sort of if you talk about the integral Hasse principle, you could, in the set of adelic points, still look at a subset of those points which are integral everywhere. And that's, again, a subset that could have no elements orthogonal to the Brauer group. So in that case, the rational points is not empty, but the integral points is empty. Because if you restrict everything to everywhere integral, then you get the empty set. I don't know if that answers the question.
Do these points obey? So these points do obey this obstruction?
Yes, yes. I mean, they are rational points, yeah. Yeah. So maybe what is a little bit unclear here is that sort of inside this set of adelic, I mean, I wanted to define it because that's the way you normally maybe write down, but inside the set of adelic points, there is also the set where the x nu are integral everywhere. And those points, those rational points, they don't have this property that are integral everywhere.
Oh, okay. So when you say there's no local points obeying this relation there, you mean no local integral points?
Right, yes, thank you. So I should add this, yeah. Right, thank you. I didn't want to write here down everything for integral points, since it's kind of useful to talk about S integral points. Yeah. And also because the kind of nice thing is that this is sort of the formulation which also, in the case of, say, X projective, reduces to the situation which is kind of well known for the study of rational points. So if X is projective, then the set of adelic points is just the product over all say, local points, and you don't care about integrality anymore. So one key observation is that this pairing is well defined only on the adelic points, but not in general on this product set. That's an observation that Colliot-Thélène and Xu in one of their papers remark as well. If you first look at these things and start off with this product, then the Brauer-Manin obstruction seems useless. That's even the word they literally use, because this pairing may not be well defined. You may not have a finite set of places for which, away from them, which are trivially zero. But it all gets solved if you're talking about the adelic points. So far, for now, with this Brauer-Manin obstruction, before I concretely talk about systems of two quadratic equations, I want to point out that there's also other things that could obstruct the existence of integral points in variety, which are some variations of, say, positive definiteness issues. I mean, of course, if you define such a thing, then you would ask, well, when is the Brauer-Manin the only obstruction, say? And if you're not careful, then you can easily come up with examples where you have local solutions, no Brauer-Manin obstruction, and still no integral points. And sort of this obstruction, say, at infinity, they turn out to be much more subtle than one may think at the beginning. That's why I want to spend a bit of time to just point out of what can go wrong here. Say obstructions at infinity. So maybe let me start with the first example. Maybe this one, 2x squared plus 3y squared plus 4z squared equals 1. This violates the integral Hasse principle. And the violation can't be explained by any Brauer-Manin obstruction. No, plus. Right. Well, there are real points, but not many. I mean, they're kind of compact, and this is not. Brauer-Manin. So in fact, Colliot-Thélène and Wittenberg in some paper even carefully work out that there is no Brauer-Manin obstruction to that. But sure, I mean, yeah, that's exactly what you say. Well, there's not many real points. So you may say, okay, well, whenever the real points are compact, then we don't have a chance to get a reasonable integral Hasse principle. So you could now ask the question, well, is this the only thing that could go wrong? So you could ask, is it enough if I say, okay, I want the real points to be non-compact? Which in fact is enough for some cases of semi-simply connected groups. So for some situations, that would already be enough. But in general, it turns out not. Right, so here clearly, this is compact. If you think a bit about these things, you will realize that if you talk about these non-compactness things, you want all real components of your variety to be non-compact. And such Brauer-Manin obstructions could cause all rational points to lie in one specific component. So if you had one bounded component, one unbounded component, Brauer-Manin could force you to be in a bounded one. So that's why if you talk about these things, one observes one should talk about all components. Another example, that's now more an informal example. The third one will be, again, rigorous. But just to demonstrate you, well, let's look at things like maybe x squared minus y squared equals 3. That has integral points, but also you have here the phenomenon that all real points satisfy, well, either x minus y or x plus y better be bounded by square root of 3. Which means if you now restrict to integral points, then one of those linear factors has to be equal to minus 1, 0, or 1. So this reduces the integral points to Zariski closed subsets. That's now, of course, a very simple example, but you could also build something which you could make a bit more non-trivial. Say, take a constant, take two forms f and g. Need not be homogeneous, and consider a variety given by the product of f times g is equal to a non-zero constant. And such varieties which need not be compact at all the real points have the same problem. So typically here again, I mean, one of f or g is then bounded by a constant, so you restrict really to proper subvarieties. So again here, integral points are restricted, typically restricted if you don't degenerate things. proper subvarieties. So the next example is an example due to Jonathan Harper's, which he discusses in a very nice piece of work on so-called log case resurfaces, which so the motivation for looking at these obstructions is that Jonathan Harper's came up with this example, well, beautiful paper, where Brauer-Manin kind of explained the failure of the integral Hasse principle, although he already had defined some obstructions in infinity which were all good. So that's Harper's 2015. So when we were working on systems of two quadratic equations, we realized that we could mimic similar examples as Harper's. We could easily build things which look completely unobstructed, which have local points, where Brauer-Manin doesn't obstruct anything, but we still have obstructions. So that motivated us to ask, well, what could be a reasonable notion B of obstructedness at infinity? So Jonathan Harper's example is given by an equation of this type plus 3 times z equals to 3x plus 1. So you kind of already see a bit, you have here this one term x, y, z, which is cubic, which appears only once. You think now a bit about the rational points, the real points that create some restrictions on them. One can show that this thing violates the integral Hasse principle. And this violation cannot be explained by an integral Brauer-Manin obstruction. So how you can see that there are no let's do that. So if you had an integer point in here, then the argument that Harper's gives is, well, first of all, you observe that z is not equal to 0. 1 is not divisible by 3. And on points, real points where x is at least 1, 11x plus 5 is bounded below by 3x plus 1, an absolute value plus 3. You stick now in the equation. So this is bounded below by 11x plus 5 times y plus 3 plus 3. And now again, this is bounded below by 11x plus 5 times absolute value of y. That's a contradiction, since that would force the absolute value of y to be 0, and that will not lead to an integral point. So there's a contradiction. So that's the proof why there are no integral points. And somehow, if you think about it, then it looks like, well, it's in a way a problem at a real place. So alternatively, you could explain it in the following way. I write this now down again because that's the new definition that I just want to put up in the next moment. So alternatively, you could observe that any real point x, y, z satisfies that either x is at most 1 or y is at most 1 or x. Sorry, that's y or z, z or y. Either one of them is bounded by 1, or if not, then you can use the equation to show that x is bounded by 9 divided by 8. I mean, x only occurs linearly in the equation, so you can imagine you eliminate for x and you figure out an x is bounded. And if I would have told you this in advance before giving you the example, then you would have said, well, the chances that you find integral points are maybe not that large for this thing. Yeah, and as I said, sort of for systems of two quadratic equations, we just ran into this problem that we would construct similar examples. So that's we decided to define the following notion of unobstructedness, which is certainly not the end of the story, but it's some attempt to rule out such examples. And it's also necessary under mild assumptions. So, well, one attempt, as I said, it's certainly not a final thing. But one definition is, say, if you take some right in projective space, so you could imagine that this thing, you could compactify it. And then you would look here at an open thing of something projective, which is how most examples in practice arise at this point. To be honest, there's a different compactification going on. So if this is an, say, irreducible Zariski closed subset, and say L some linear form, so say you could compactify this with a variable t, and then you could take here the linear form L equals t. And then we would say, okay, we have the hypersurface where t is 0, that would correspond, well, also live in Pn. And then we would be interested now in the set U, which is the complement of x minus h. So where here, if you would compactify it, t is not 0. That's the situation. And you should think of this U as that variety U over there. And then we call U strongly unobstructed at infinity. If every component U dash of the set of real points fulfills the following condition. So in a way, we want to rule out that there are some functions for which at least one of them is always bounded. And one way to say this is the following. So you could say, given any degree d and finitely many forms, so of these forms, I'm thinking about, say, the coordinates x, y, z, or the functions f and g, or x minus y, x plus 1 in the above examples. So and for any finitely many such forms that you can come up with, say, call them S1 up to SR, or formally maybe take global sections of the sheaf O of D. And of course, your functions shouldn't be constant, which in this language translates to you don't want any scalar multiples of, say, L to the D. And for every constant C, then you always want to find a point, a real point in the component, such that all of those functions, if we have decided that L is equal to 1, it would just be the function here itself, is pointed by a constant for all I between 1 and R. So this notion would explain all of the above examples as obstructed. So for example, this x minus y and x plus y would be two functions, or in Harper's, the three coordinate x's, or f and g, the example in between. In a way, this is a very reasonable assumption, since if this condition is violated, then one can show that, at least in the situation that U has only one real component, then integral points cannot be Zariski dense. In U. So that's at least some now condition where you could ask, okay, if you assume the stronger version, now it makes again sense to ask for what families is, say, Brauer-Manin the only obstruction to the integral Hasse principle. And now I finally want to come to the concrete situations of two quadratic equations that I was studying with my collaborator Joerg Jahnel, with whom everything here is joint work, and give you discuss sort of a bit what we know about integral Brauer-Manin obstructions in that case.
Sorry, the C is arbitrary, and the point is this is an unbounded sort of condition.
Yeah, exactly. Yeah. So that's just one way to formulate what we see. It's one way to write this down. Exactly. So let's now talk about systems of two quadratic equations. So everything what I'm talking about is joint work with Joerg Jahnel. So the situation that we were interested in is that they take two quadratic forms, Q1 and Q2, with integer coefficients, say in variables x0 up to x4. So let this be quadratic forms. And then you can consider the subscheme, the open subscheme in P4, which is given by Q1 is 0 and Q2 is 0, and say x4 is not equal to 0. So if I write it down in this way, and if I ask now about integer points on that scheme, then this corresponds to solutions x0 up to x4, where x4 is equal to plus or minus 1. So that's the notation, what you should think about if you talk here about integral points. Then integral points on U correspond to solutions x0 to x4 in set 5, where x4 is equal to plus minus 1. So this comes just from the way that I formally define this as a schema of spec set. So if x4 had some other divisor, then if you would reduce it modulo p, you would then land here in x4 equals 0, which is a thing that we avoid. But that's just merely a thing of notation. So concretely, that's the situation of having two quadratic equations. They may be non-homogeneous, as you said, x4 to say plus minus 1 in 4 variables. Then you can ask, well, can we describe the Brauer group? And if you can describe it, can we describe the obstruction that it causes? And that was sort of the main line of investigation. So the answer is that we can describe part of the Brauer group, and another part remains somewhat mysterious. Namely, there's a filtration of the Brauer group in sort of 3 parts. So first, let's say U is again this variety where I consider it as a variety of the rationals. We have a filtration in the following way. In the mild assumptions, the Brauer group of U, it always contains the Brauer group of the rationals. That's a constant algebras. But they don't do anything. So if you pair them with any adelic point, you get always 0. So that's not a very interesting part. Then there's another part of Brauer group, which is initially noted by Brauer-1, which is so-called algebraic part of the Brauer group, which sits inside the complete Brauer group. Formally, this Brauer-1 is the kernel of all the elements in the Brauer group, which disappear if you base change U to some algebraic closure. So in our examples, the one quaternion algebra, which we've seen before, would be an example of an algebraic Brauer group element. So remember, that was some function comma n, this kind of quaternion algebra. If you now join square root of n to the rationals, then this completely splits and the obstruction disappears. So that would be an example of an algebraic Brauer class. So there's this filtration, and ideally we would, of course, understand the complete Brauer group, but the first question is determine this part of the Brauer group of the algebraic classes. So maybe something that I could say is that if you would consider the homogeneous situation, so if I just consider the system Q1, Q2 equals 0, two homogeneous quadratic equations, then this defines that it has a surface of degree 4, which are well-studied things, and for them, there is only an algebraic part of the Brauer group, so that we will get more something specific to the situation and also to now looking at integral points. And but still, we can first of all describe the algebraic part of the Brauer group. And you find that there are the following possibilities what can happen. So let's say X be a degree 4 by a Pezzo surface. So the intersection of two such quadratic equations. Additionally, assume that the intersection is smooth of codimension 2. And let's say H is a Q-rational hyperplane. Above given by x4 equals 0. And we need to assume that the intersection of H with x is geometrically irreducible. And then let U be the complement of x minus h. Then this part of the Brauer group, Brauer 1, is isomorphic to one of the following. Well, either it's trivial, or it's a product of Z modulo copies of Z modulo 2 set, and you can have at most 4 of them. So for some k between 1 and 4, or you could have some 4 torsion in there. You could have a Z modulo 4 set cross a Z modulo 2 set to the power L, say. And now for either you don't have another copy, or you have at most 2 copies of another Z modulo 2 set. So that's a description of what these Brauer groups can be, which can cause some obstructions. The harder part of the project is to explicitly describe these elements in the Brauer groups. I mean, only to compute them is more the thing which is much easier. In almost all of the cases, we can also give explicit descriptions of the elements in the Brauer groups by Asamaia algebras. And there are two harder cases where we can show that, in a certain sense, simple descriptions by such just quaternion algebras are not possible, but cyclic Asamaia algebras, which can globally be written down as such a non-residue symbol. Right, that was sort of the next one of the remarks that I want to, exactly put down here. So, due to calculation of Schindler and Dyer, if you only would look at homogeneous things, so if you don't take out this hypersurface, just look at Brauer X mod Brauer Q, then this is isomorphic to either 0, Z modulo 2 set, or a product of Z modulo 2 set and Z modulo 2 set. So in particular, if you have already a Brauer group in X and then remove a hyperplane, then this stays in U. But you get more things if you remove a hyperplane. You can somehow think about it if you can construct them. You start with some Asamaia algebra, which is first defined on an open subset of your variety X. And to make it into an element in Brauer group of X, you would need to show that you can cover your variety with open patches and have Asamaia algebras defined in all of them such they glue together. And so it's now kind of intuitive to see that if you take out a divisor, if you remove a hyperplane, then it's easier to extend Asamaia algebra to the whole of U, because you have one divisor less where you can still have poles of your Asamaia algebra or zeros, which you don't have to be able to cover. And so that's in practice where it comes in. You also see that in the theorem there are many more possibilities now. And yeah, if you want to evaluate them, you will figure out that the processes are much more complicated. How much time do you have left? Okay. Well, also the whole thing works over any number field I could mention. But now let me address this question of how about the transcendental part? Well, we know something about it. So first of all, following some classical theory, we can deduce that if u, x, and h are as above, and additionally assume that the intersection of the Pezzo surface with the hyperplane, let's call it D, if this is non-singular, then the transcendental classes, modulo these algebraic classes, which we do understand, they embed into the torsion points of the Jacobian of the variety D, into the Q-rational torsion points. So where here J of D is the Jacobian variety of D. So this x is given by the intersection of two quadratic equations in 5 variables. If you say now set one variable equal to 0, which would correspond to intersecting with h, then you end up with two quadratic equations in 4 variables. And then generically, this defines your genus 1 curve. If this has now a rational point, then you would have an elliptic curve for D. And then we would observe that all transcendental elements in the Brauer group can, well, give rise to a torsion point on the associated elliptic curve. But the other way is completely open. We have no idea which elements, which torsion points give rise to an element, transcendental Brauer group element. So that's a direction which we don't know. In general, Colliot-Thélène, Bogatov have studied that question. So for more general situations of smooth projective varieties, this is not projective, but well, so in other situations, they can bound a co-kernel, but in general, we also don't understand which ones, not even in concrete situation, which ones really descend to transcendental Brauer group elements.
So do you have examples with transcendental?
Yes. So that's exactly the next thing that I want to mention. So yes, we are able to construct families where this is the case. We are not able to, so if you start with the divisor, say, and give me a torsion point, we are not able to construct a transcendental Brauer class, but we are able to construct families where these things do occur. So. Sorry?
In general, there's no up, here, and down in the order of these torsion points? Expecting, like...
Well, I mean, you have got... I mean, I don't know any results, sort of, say, for the Brauer group to have bound on the torsion elements, no. I mean, what you could do is you could bound with similar arguments as Colliot-Thélène, Bogatov of the co-kernel, if you wanted to. But no. So we can construct families with transcendental Brauer classes. Yeah, that would be in the spirit of our conjectures. I mean, they don't apply to these situations since U is not projective, but I mean, U is, in this case, that we are considered a so-called log K3 surface, which if you study integral points in log K3 surfaces, people tend to compare this to the situation of rational points in K3 surfaces. Sort of in this analog situation, yes, we do expect boundedness. So yeah, if you're optimistic, you could say, okay, it's maybe the same here. So I just want to give you one example, and the family will then be clear sort of how to construct more of them. So one example where such a transcendental obstruction occurs is the following system of two quadratic equations, which are now sort of in a way of want to represent a tuple of two integers by two quadratic equations. And I don't multiply these things out because this, what I'm writing now down, is the form the family that we can produce in general, x0 squared minus 8x1 is equal to 3, then this is an example where this violates the integral Hasse principle. Due to transcendental Brauer-Manin obstruction, or better to say it can be explained by transcendental Brauer-Manin obstruction. And the Brauer class is given by, again, as a minor algebra, which, or the function field looks like 8x1 plus 3 and 8x3 plus 2. And also I want to remark that this thing is strongly unobstructed in infinity, so there's no kind of real reason why you wouldn't find an integral point on this. We don't know of an elementary proof, yeah. Maybe there is, but we don't know. I mean, sort of this unobstructed, that rules out that such an elementary proof at a real place works exactly, yeah. So the general family that we can write down, you already see sort of if I write this term on the right-hand side, then I have here a linear form 3x2 plus 2, which I repeat here. And there's a linear form 8x1 plus 3, which we repeat in there. And then we have, yeah, here 2 squares of 2 linear forms and 2 other arbitrary linear forms, and that's the family that we construct. So you can replace all of the linear forms up to some non-degeneracy conditions with anything. You will always find exactly this Brauer class in the family. So for the final few minutes, I want to say a bit about how often would you expect to see a non-trivial Brauer group. So if you were given 2, say, generic systems of quadratic equations and 4 variables, yeah, what would you think? Or how would you recognize? How could you recognize them? That's, in fact, sort of the place where then also analytic number theory goes into the work, which I will not have the time to discuss today, but I just want to get you to a point to see how you can, at some point, also get quantitative estimates. So you could ask the question, how often do we say expect? Maybe Brauer is a bit optimistic. Maybe we'd rather talk about the algebraic part here. But still, let's ask the question, how often do we expect this to be non-trivial? So there's one criterion that you can exploit also analytically. And for this, we first have to elaborate a bit further on the things above. So assume that x is, say, given by 2 quadratic equations. Now I want to write them in sort of in matrix form. Say A and B are the 2 associated matrices for the quadratic forms Q0 and Q1, where A and B are both, say, 5 times 5 matrices. Assume some non-degeneracy, such that this is smooth of codimension 2. Then you can associate the characteristic polynomial f of lambda and mu, which is the determinant of lambda times A plus mu times B. So f will be 0 if and only if the element in the pencil of those 2 quadratic forms has rank at most 4. And so of degree 5, and in the generic situation has exactly 5 roots, corresponding to exactly these 5 to generate quadratic forms in the pencil. And one criterion, which is sort of a corollary from the description of the Brauer group and all of the subsequent considerations, as the following sort of corollary or theorem comes out of the same ideas. So let's take everything as above. We can say that if we find that there is something non-trivial in the algebraic part of the Brauer group, then this characteristic polynomial f of lambda mu is reducible over the rationals. And with this criterion, you can get some bounds on some model families on how often do we expect such an obstruction. So first of all, this condition, if you look at a suitable model family, gives you that the exceptions where you can have a Brauer-Manin obstruction are thin sets, but we can even get somewhat better bounds than that. So one model family that we did study is the following. So fix, say, one of the matrices A with maybe determinant of A not 0. And then define a set n Brauer. So call this equation, say, star. We could count and say, OK, let's count the matrices B with, say, integer entries, which are symmetric, and where all the coordinates, which I call Bij, are bounded by P, and such that this variety is smooth, is really at the Pezzo surface of degree 4, so smooth of codimension 2, and such that the algebraic part is non-trivial of the Brauer group. Then this number of total matrices that you could count is above P to the 15 things. You have 15 entries if you postulate this thing is symmetric. And we get a power saving of the things that could have some Brauer-Manin obstruction by B to the 14 plus a fifth plus epsilon. And that's coming out from some analytic methods. So in fact, how we approach this theorem is we compare it in a way to a situation of, say, study a polynomial in one variable and ask for its Galois group. And say if you have a degree n polynomial, if you average over the coefficients, typically you expect Sn as the Galois group. And all the other subgroups are exceptional. And a similar line of approach also leads to estimates on how often a Brauer group can occur in using this reducibility criterion. Yes, exactly. P to the 50.
That's a 1/5. Right?
Yes, yes. No, sorry, yeah, it's a 1/5. Yeah, right. Right. So that's the approach that we take. If you would just say, OK, it's a thin subset what these conditions describe, you would get here by large CIF estimates P to the 4 times plus a half. So you can get some improvement. And you should get some further improvements if you talk about 4 torsion, or if you, yeah, so there's still some room. OK, I think that's all what I want to say. So thank you for your attention. Yeah, that would be a natural thing to ask, right? But to be honest, we don't have evidence for or against. So yeah, you could compare it, say, to K3 surfaces. So these are examples of log K3 surfaces. And studying integral points in log K3 surfaces very often is compared to studying rational points in K3 surfaces. So motivated from that, you may say, yeah, let's conjecture that's the only obstruction. I mean, that's also the way kind of how Harpers came up with his example. So he modeled such a conjecture and then said, oh, that's a counterexample to my conjecture. And so at least that's why we really made a point of strengthening this obstruction at infinity to give such conjectures a chance to be true.
Any other questions?
Yeah. So can you say something about when you're counting parts in the transcendental Brauer group is trivial? Because I mean, generically, this portion group, I mean, the total probability curve is going to be 0.
Right, yeah, we didn't do that yet, but yeah, anything you can feed into the right-hand side on how frequent you see torsion, you can feed it into results of the transcendental part.